Good, thank you. All right, so my name is Brendan Whitney, master's student here at the University of Arizona in the GIST program. And I am going to be presenting on my capstone project, determining the impact of human infrastructure on the Mexican wolf in Arizona and New Mexico. During this presentation, I'm going to be talking about the background of my project, specifically looking at the history of the problem, previous research that's been done in this area, the objectives that I set up for myself, and the study area that I'm using. I'll then jump into talking about the actual analysis with the data and the methodology that I used. And then I will be talking about the outcomes, looking at the results and the conclusions I have based on those results. The Mexican wolf is the smallest and southernmost gray wolf subspecies in North America, and it formerly ranged from southern Arizona and New Mexico down into southern Mexico. However, because of conflict with humans, primarily over livestock, this subspecies was nearly driven to extinction with an estimated population of less than 50 wild wolves. After the US Fish and Wildlife Service listed the Mexican wolf as endangered in 1976, captive breeding programs and reintroduction efforts have led to more than 200 wild wolves in Arizona and New Mexico as of last year, with more in Mexico. There are some controversies related to the reintroduction efforts, especially with ranchers in the region. There's been a lot of research in this field. While researching, I ran across two studies that inspired this project, both of which had Martinez-Meyer listed as the first name. Both studies performed habitat suitability analyses across the historical range and are considered to be some of the best research in this space. To perform their suitability analysis, they use such variables as land cover, climate, topography, food availability, human population density, and road density data. The primary variation in their studies is the inclusion of food availability data in their analysis, which impacts the results of the habitat suitability analysis. That leads me to what I want to look at. I wanted to create a habitat suitability model that was comparable with the Martinez-Meyer studies, meaning that it should use similar data and should have similar outputs. However, I wanted it to allow for variable weights so that I could look at the impact of human-related variables on the final outcomes. This emphasis on human infrastructure is based on the historical reason for the near extinction of the Mexican wolf, which is human interaction. I was anticipating that increasing the weight on the human-related variables, population density and road density, would decrease the amount of suitable habitat in the region. The study area I used for my project is the Mexican Wolf Experimental Population Area, or the MWEPA. The MWEPA, as outlined by federal law, consists of all of Arizona and New Mexico south of Interstate 40 and contains 3 zones. Recovery efforts are currently focused on Zone 1, which you can see there in green, and it is made up of various ranger districts within the Apache Sitgreaves, Gila, Tonto, and Cibola National Forests. It is important to note that the MWEPA contains only a part of the land formerly inhabited by Mexican wolves. Mexico also contains large tracts of highly suitable habitat, especially in the Sierra Madre Occidental. However, I chose to use the MWEPA based upon my familiarity with the region. Now let's dive into the analysis portion of the presentation, where I first talk about the data that I used. The 2021 iteration of the Martinez-Meyer Habitat Suitability Study provided additional data that could be used for open research, including a CSV file containing historical locations of Mexican wolves separated into primary and secondary records. I used the primary records to train a presence-only prediction model, or MaxEnt model, for climate variables within ArcGIS Pro. All I had to do was convert the CSV file to a point feature class using latitude and longitude data that was included, then filter down to the primary records. The Martinez-Meyer study used several climate and topographic variables in order to run their prediction models. I was not able to get the same climate data set that they used in their study, but the Climond archive provides several raster files with similar variables over the entirety of North America. They used 12 climate variables, and I was able to find 8 that corresponded with those climate variables in the Climond data set. You can see the variables that I used in the table on this slide. I also used the Hydra 1K data set for topographic data, which includes elevation and slope. I also used the terrain roughness index, which I had to derive myself from the Hydra 1K elevation raster image using GDAL in Python. The next data set I used is land cover data from the European Space Agency. This is the exact same land cover data set that the Martinez-Meyer studies used. As you can see, it shows vegetative land cover across the study area. Like the Martinez-Meyer study, I used a population density raster from the Center for International Earth Science Information Network. However, I was not able to find the exact version they used, so I used a slightly updated version of their data set. In their study, they scaled suitability based on a threshold value, with higher population density values being less suitable and lower population density values being more suitable. They presented 3 different thresholds, of which I used the intermediate value of 3.13 people per square kilometer. The areas in dark green on the map are those that are more highly populated than that threshold, meaning that they are less suitable. The last data set that I used in my analysis was road density. Like the Martinez-Meyer study, I used data from the OpenStreetMap. However, like the population density layer, because of the constant updates to the data set, I used a more recent version of that data set. In order to prepare this data for analysis, I had to filter the data set by road type and convert the vector lines to a density raster. Also, like population density, I scaled the road density values around a threshold from the Martinez-Meyer study, which is 0.445 kilometers of road length per square kilometer. This leads me to the methodology that I used in my analysis. I first had to prepare the raster data sets for the analysis by reprojecting each into the same coordinate system, resampling them all to the same spatial resolution, then clipping each to the study area. I first performed a presence-only prediction model based on the climatic variables and the elevation products using the Wolf location points as training data. This tool finds the best conditions in the input data based on the training conditions or training points and outputs a raster, which in this case represents the likelihood that wolves could have historically been in those areas based on the input topography and climate conditions. I then rescaled the output of that model, the population density output, and the road density output to a range of -1 to 1. In each case, a -1 represents the least suitable condition, while a +1 is the most suitable. I reclassified the land cover data set based on values given in the Martinez-Meyer studies. The classified values fell in the same range of -1 to 1 with the same meanings. Once all data sets were scaled to the same range, I was then able to perform a weighted average. The Martinez-Meyer study uses an additive method where they have different scales and they come to a larger number range. But because I use a weighted average method, everything fell within the same -1 to 1 range. The resulting values are on that same scale. On this slide, You can see each of the different weighted averages that I took. I use 4 different combinations of weights, one where all weights are equal, one where row density is given 2 weights, one where population density has 2 weights, and the last where both population and row density are given 2 weights. In all equations, output ranges have that same maximum range. In the results, I will primarily focus on unweighted and weighted maximum models, which are bolded in that table. For ease of interpretation, I set the threshold for highly suitable habitat to a value of 0.75 or higher, meaning that range of 0.75 to 1 is considered highly suitable. This corresponds with the upper 1/8 of potential values. So this map that you're currently looking at shows the comparison of the results of my unweighted model and with those of the Martinez-Meyer studies. The unweighted model produced 31,500 square kilometers of highly suitable habitat, while their study produced 33,000 square kilometers within the MWEPA. As you can see, suitable habitat was found to be generally in the same areas, indicated by the dark gray color. Regions in orange are those areas that only my model found to be highly suitable, while areas in blue were found to be highly suitable only in their model. For example, areas near Eager and across New Mexico are better represented in the Martinez-Meyer study than in mine, while mountainous areas near Sedona, Sierra Vista, and Gallup are better represented in my results. Overall, including differences, I felt that my model behaved similarly enough to theirs for me to continue with my objectives. The map that you're now seeing shows us the difference between the unweighted model and the weighted maximum model to show the impact of human population and row density. In the table in the lower left corner, you can see that there is a large difference in the various models, with the unweighted model showing 31,500 square kilometers of highly suitable habitat, and the weighted maximum model showing 43,500 square kilometers. The increase in the quantity of highly suitable habitat from the unweighted model to the weighted maximum model is especially evident in the areas between Flagstaff and Eager in Arizona and to the southwest of Socorro in New Mexico. Overall, there were some large differences between my results and the Martinez-Meyer results. A big part of this probably came from the data that I used. The biggest difference in data between my study and theirs is the number of climate variables. They used 12 and I used 8. The missing temperature and precipitation variables could easily explain the inclusion of lower elevation areas at different latitudes within the study area. Additionally, I only trained my model using points within the MWEPA, whereas they trained their model with the wolf location points across the entire historical range. So areas in Mexico do not impact my final results. 2 of my data sets were also more recent. Finally, some of the discrepancies may have come from the difference between their additive model and my weighted average model, and the threshold I used to determine what is highly suitable. Contrary to my earlier assumptions, an increase in the importance of human and row density in the calculation increases the amount of highly suitable habitat. This is not what I expected, but upon further consideration, I came to the realization that because much of the MWEPA is very sparsely populated, the increased weight given to population density boosts the total amount of suitable habitat. Further research into the needs of Mexican wolves, the impact of their reintroduction, and the factors that lead to the success of populations can better inform recovery efforts. Examples of possible research related to this project include the suitability of habitats when considering grazing rights within the study area to account for conflict with ranchers that occurs today, and the impact that human population and road density have in the entire historical range of Mexican wolves, not just within the MWEPA. Thank you.
Great job, Brandon. That was a really amazing analysis. It was very thorough. He's integrated all kinds of different types of data. And I really like that you compared it to an existing study and found different things. That's a really great way to make sure your methods are sound while still improving on different things. I guess the question was, since you compared your findings so closely to the Martinez study, what do your findings say, or how would they influence policy in a different way than the Martinez study? Is there something that your work could help inform certain aspects of sort of management regarding wolves that the Martinez study couldn't, or vice versa?
That's a great question. A lot of policy right now is based on the fact that this is an experimental population area. So even though this is an endangered subspecies of wolves, a lot of the conflict between humans and wolves is not as highly, regulated, as highly punished as it would be if it were not an experimental population area. So because we're taking a look at the impact of road density and population density on the analysis on the suitable area, really it allows us to start looking at those areas specifically that would be especially good suitable habitat for the Mexican wolves. Knowing that human population density and road density seem to have an inverse relationship, where an increased importance on those factors contributes to more suitable areas. I think turning towards other factors such as grazing rights, it would be a better use of time when coming up with future policy decisions.
Perfect, thank you.
Hi, Brandon. I just wanted to say, first off, great job in your analysis. I like in your conclusion how you sort of indicated that maybe looking at some of the land use categories that can be associated with these potential habitat areas would probably be a good thing to look at just because of the conflict with humans. But I had two questions. One was, what was the cell size of your data that you were looking for your various layers?
I used 1 kilometer pixels.
Okay. Yeah, because that would be one of the things I'd also wonder is if you had any insights to maybe using different levels of scale data. I know when you're doing a really large area, you have to find a reasonable number, but if you wanted to use the model in a larger scale, more localized areas, what kind of recommendations you would have for the level of detail you think would be great to pull out these potential habitats and where conflicts might arise?
So when it comes to the spatial resolution of the study, I used 1 kilometer because it's a nice round, easy to understand number. And I do feel like as long as the computing requirements are sufficient, 1 kilometer would probably be appropriate across the entire historical range. However, looking at a larger, or rather coarser spatial resolution, we would probably want to that would generalize the data in a lot of areas. So if we're looking for a more generalized look at, so we've done it at 1 kilometer, let's say we want to do 10 kilometer pixels, what impact does that have? I imagine that many of the areas that were included in this area might not be included, just because much of the areas around these islands of suitable habitat may not be